Hello everyone, so this is part 2 of your pressure video lesson. So previously we have introduced to you the formula for pressure, and then we did a bit of a simple pressure question involving solid. So I already tell you that is for level 1 difficulty, whereby you need to explain why do you have certain design feature. Sometimes it is to lower the A, sometimes it's to increase the A. Do you recall what A stands for? So does A stands for base area, contact area, or surface area? So I think by now you should remember that A is contact area between something and something. So basically for level 1 difficulty, they will ask you about the design feature, and you have to use this formula P equals to F over A to explain that why having a large area will give you certain advantage, things like that. Then after that, we spend the second half of the lesson to talk about some level 2 question, whereby it is pressure exerted by a liquid. This liquid, it is trapped between two pistons, and we say that due to the property of liquid being incompressible, when you apply a force on the piston on the left, the pressure generated would be transmitted to the other piston, and if the area of the piston is different from one another, we could amplify the force, or we could reduce the force. Okay, we can manipulate the output force. Now this manipulation of course has a cost, and the cost is that the distance traveled by each piston. So for example, if this piston travel by 1 cm, if you have a different area, then the piston on the right will be traveling at a different distance. So can you recall what is the working principle for a hydraulic jack such as this? Besides pressure on the left is transmitted to pressure on the right. Yeah, so for the second principle is that the volume displaced by the left piston must be the same as the volume created on the right hand side piston. So for any hydraulic question, basically you can use these two equations to actually solve the calculation. Of course, these two relationship, we are assuming 100% transfer. So for example, if there is air bubbles inside the liquid in a hydraulic jack, then the bubble being compressible will actually take up some of the pressure, and so less pressure will get transmitted. So if there is an efficiency, you will put it on the left hand side. Now today we are still going to talk about pressure involving liquid in fact, and we are going to learn one new formula. Then after that, we are going to talk about two instruments called barometer, and then we are going to talk about another instrument called manometer. Yeah, we are still going to use your worksheet 7.1, so get it ready. So let's get started. Last lesson, what we have is that we have liquid trapped between two pistons of different cross-section area, and we are able to actually make use of pressure transmitted in liquid to achieve some amazing result. For example, we amplified input force to a much larger output force. Now this lesson, what we are going to do is that we are going to examine how pressure in liquid actually behaves. So for example, if now I have an open cylinder and I put liquid in, and I wanted to find out what is the pressure exerted by the liquid at the base of the cylinder. Okay, I want to know what is the pressure. Now in this case, then the pressure at the bottom here will be experiencing a force over the area, which is here. Now what is this particular force that this area is experiencing? Well, the fluid on top has mass, and that means it has weight. So basically what is acting on the bottom of this cylinder is the weight of the liquid. So actually we can rewrite the equation to be this. Now before I carry on developing this equation, what I'm trying to do here is to show you how do we arrive in an expression that will tell you the pressure exerted by a liquid fluid. Okay, so let's carry on. So the weight is given by the weight of the liquid is given by mass times gravity, right? Yeah. Now what we are going to do is that we are going to look at the mass in terms of density. Yeah. So what we know is that your density is given by mass times volume. So this symbol here is called rho. It is the symbol for density. Now since we know density is universal, is a constant, is a property constant, then the mass of this can be given by density times volume. So far so good? So once we have that, we can rewrite our equation as this. Now if you remember, the volume of a cylinder is given by this equation, right? Volume is given by cross-section area multiplied by the height of the column. So for example, if now my liquid column is like a cylinder, then I just need to take this area and then I multiply by the h, the perpendicular h to the base, right? So if I know that, then this formula would become like this. Now what you notice here is that after we manipulate this, can you see that the cross-section area, the A, will actually get cancelled out? So because of that, we actually make use of this formula, rho GH. So this pressure formula is for pressure exerted by a certain liquid column. It is equals to the density of the liquid multiplied by the gravitational strength and the vertical height. So for example, if you are swimming in a swimming pool, let's say the swimming pool get deeper and deeper and you are swimming down here. When you are swimming here, you are actually being pressurized by the fluid on top of you. So of course, if you dive deeper and deeper, you can see that, okay, on top of you there are more and more layers of water. So if I wanted to actually find out what is the pressure that you are experiencing, I can just take the density of the water, multiply by the gravity, and finally multiply by the h measured from the surface. Now, is this the total pressure that you are experiencing? Well, let's take a look. For example, if you are standing on a flat ground, are you experiencing any pressure? In fact, yes. On top, around you, there is fluid. So what is fluid? Fluid can be any liquid or gas. So around you, there's air from the atmosphere. So actually, you are actually under a lot of pressure. The pressure acting on you by the atmosphere is equals to density of the air multiplied by G and multiplied by the thickness of the entire atmosphere to the sea level. So if you multiply all these things together, the atmospheric pressure is about 100,000 Pascal. So you may be asking me, wow, we are under so much pressure, how come we are not feeling it? Well, there are two reasons. The first reason is that inside your body, there's gas as well. So in your gas, in your lung, there's pressure. So what happens is that this pressure actually balance off with the pressure outside. What happens if your lung does not have enough pressure, then you will be squashed. The other way around is also true. If you are flying on a plane at a very high altitude, because if you are flying very high, that means the thickness of atmosphere on you is very little. So actually, the higher you go, the lower the atmospheric pressure. So I mean, if you have here this phrase that if you are flying a plane, the chamber inside the plane is actually pressurized. Why? Because if you are flying on a plane at a very high altitude, the surrounding pressure around the plane is actually very, very low. And if we do not keep the cabin pressure, you will find that your body's pressure will be larger than your surrounding pressure, and of course your eardrum will not be feeling very good. So similarly, if you are diving in water, what happens is that the surrounding pressure, the outside pressure, will be higher than your body's pressure that's inside. So your eardrum will actually get pressed inside, so you will feel the pain. Similarly, when you are taking off on a plane, the surrounding pressure will be actually lower than your inner pressure, your body pressure, and then your eardrum will be popping out. So either way, if you don't equalize the pressure, you will feel your ear will be sensitive enough to pick up the change in pressure. Another reason for why you are not feeling this 100,000 Pascal from the atmosphere is because you are born into the atmosphere. So when you are born, and because our body structure has evolved to actually adapt to this kind of pressure, you don't feel it. But if you dive deep into the water, your body is not conditioned to do that, and you will feel the pressure around you building up. So technically speaking, even if you are standing on a flat ground, you are under 100,000 PA. So if there's a question asking you what is the pressure that you are feeling when you are under a certain liquid level, you have to add in the atmospheric pressure. So actually, when you are diving, your body is actually under this amount of pressure. Okay, now that we know that your fluid pressure is given by rho GH, you will notice something that is very interesting, that in this formula there is no more A. This means that if you have two cylinder, one big, one small, and you fill it up with the same amount of fluid of the same density, and if you are standing below, regardless of the cross-sectional area, whether it's big or large, as long as the density is the same and this vertical height is the same, both of them will actually have the same amount of pressure acting on them. Now this is also true if you have like a super weird kind of cylinder like that. As long as you fill it up till the same height, the pressure underneath will be the same, because the pressure of a fluid column is defined by rho GH. So for example, if now I have this, and if I have this, if I fill it to the same column and you are underneath here, will PE and PF be the same? Yes, they will be the same, because as long as the vertical height here is the same, then according to rho GH, if the density is the same, G is the same, H is the same, then the pressure experienced by the bottom is also the same. Yeah, so this is one very important feature. Now, another important feature about liquid reacting to pressure is that the liquid will always flow in a way to equalize the pressure. Now, what do I mean by this? Imagine if you have a bucket that is like that, and when you pour water in, will the water level becomes like that? No, right? If you pour water into an irregular shaped chamber, somehow the liquid level will spread out, and that is because your surrounding pressure, atmospheric pressure, will act equally on every surface and will push the water level down. It will spread out nicely. Now what scientists see in this is that they make use of this and come up with this thing called a barometer. So let me explain to you how this barometer works, and it is very important that you learn this, because this will also introduce to you one more unit for your pressure. So I want you to imagine now that I have a bucket of mercury. So if I pour mercury in, the mercury will just fill up the bucket, right? Nicely and flat. Agree? Now what I'm going to do is that I'm going to insert a tube with both ends open into the mercury reservoir. Now when I do that, what would happen is that, well, the mercury will go into the tube and fill it up. Now because the tube is open on the top, basically everywhere on the surface will still experience atmospheric pressure, and so it will be flat, right? Now what if now what I'm going to do is that I am going to seal up one end of this tube. So it is sealed, only this side is open up. Now when I do that, then okay, the thing will be still going in. But what if now after I seal it up, I try to suck out the air that is trapped within the mercury, within this tube. Now when I suck out the air, what happens is that the mass of the air inside this tube will reduce, and of course the number of particles per unit volume will drop, collision frequency between the molecule and the wall will drop. So as a result, the pressure that is inside this tube will be almost zero if now I remove the air. So what happens is that this pressure in the tube will be almost zero. Now something interesting will happen is that while I do that, the pressure outside is actually the P atmosphere, which is a big value, about 100,000 PA. Now because fluid can move, so what happens if down here I am pressing down hard with the atmospheric pressure, and down here inside I have almost no pressure and I have empty space? How would you think the mercury will react? The mercury will start going into the tube and building up itself, right? But will this mercury liquid rise infinitely? Well, it depends, because as the mercury column rise over here, the mercury down here will get heavier and heavier, and what is supporting this mercury column is the pressure outside that is pushing the mercury into the tube. So basically this column height is an indication to how much pressure that is on the outside here. So what happened is that we have built this simple device whereby I basically have a reservoir of mercury or any fluid, and I put a tube like that, and then I fill this thing up, this mercury, I fill this reservoir up with mercury, and of course I have to make sure that here I vacuum it. Basically I remove all the air that is inside here. Now when that happens, the mercury column will start going into the tube, because on the outside the atmospheric pressure is pushing the liquid into the tube, right? And it will push them into the tube until the liquid column that is in the tube is just nice being supported by down here, the atmospheric pressure. Meaning to say, if my atmospheric pressure is very high, my column that can go into the tube will be taller or shorter? It will be taller, right? So actually we actually can make use of an equipment like that. If I see that this mercury column height is tall, then we can conclude that the surrounding pressure must be high. So we use this instrument to actually measure our surrounding pressure. So this is a concept. So how do we measure exactly? How do we get a number? Well, we say that the pressure here, this red dot, and the pressure here inside the tube has to be the same. So we usually call this P1 and this is P2. So if I look at this, P1 is equals to P2, right? P1 is being pressed down by the atmospheric pressure. P2 is being pressed down by vacuum. Well, vacuum has no air particle inside, so no pressure. That means P2 is the pressure experienced by P2 is solely given by this liquid column. And we have learned how do we calculate the pressure exerted by a liquid column, right? We use rho GH. So when we do that, we actually find out that, oh, this rho GH and this atmospheric pressure will produce the same pressure. Now, it is sometimes, if I have to make use of this and then I have to multiply density of the fluid and multiply by the height and everything to give me a reading in Pascal, it is quite troublesome because we have to use calculator and all, right? So what the scientists do is that they use this equipment and they measure the pressure in terms of cm Hg. Now what is cm Hg? Basically they just put a ruler over here and basically they measure the height. So if under atmospheric pressure, most likely it will support a mercury column that is of 76 mm Hg. Okay, so it will support a column of 7.6 cm. So we say that, oh, okay, the atmospheric pressure is basically 76 cm Hg. That's all. Okay, so what is Hg? Hg is the fluid that is being used, and Hg is the chemical symbol for mercury. So most of the time your barometer, they make use of mercury, and then depending on the surrounding pressure, it will support a certain column of mercury over here, and basically we measure the atmospheric pressure in terms of how tall the liquid column is. So this 76 cm Hg is basically telling you that, oh, the atmospheric pressure can support 76 cm height of mercury column. So for example, if you decided to climb a very high mountain, so when you climb a very high mountain, when you reach the top, you're actually under a very thin layer of atmosphere compared to when you are at the bottom, where you are under a deep layer of air. And if you bring a barometer up here, you will find that the mercury column that can be supported will be way less than 76 cmHg. Now you may ask me, teacher, then how to convert cmHg to Pascal? Well, it's the same. If you know that you are under 76 cm height of mercury, then you just take mercury's density times the G, which is 10, and then multiply by 0.76. So just remember your H here should be in meter. Yeah. So now that is the basic concept of a barometer, and of course, the other thing you need to recall is that, oh, okay, now we know that fluid will flow to actually equalize the pressure, and pressure can be measured by cmHg. So now can you take out your worksheet 7.0, and we are going to consolidate our learning in the worksheet. Okay, so now we are back to the worksheet 7.0. Let's go back to the first page. So like I said, the other unit for measuring pressure is that we measure the pressure in terms of how high a mercury column that it can support. And like I said, there are two measuring instruments for pressure. Today we are going to cover the barometer, which we have done so, and that is that vacuum tube thing in a reservoir of mercury, right? The other thing that we are going to talk about in today's lesson is called a manometer. It is very similar to a barometer, so we are going to talk about that later on. Okay, so let's flip to your page 4. So for your page 4, basically for 6a, this question is to actually ask for you to consolidate how do you change P equals to F over A into the liquid pressure formula, P equals to rho GH. Now, is this tested? Lucky you, this is not tested. Will it be good for you to know? Yes, it's good for you to know. So down here, I will just put down so that you don't need to flip in your book how it is being developed. So it is like this, W over A, W it becomes mg, and then the m become density times volume, and then after that it volume become AHG over A. So finally it will become rho GH. So down here I have given you all you need. So this to here, this is because is density is equals to mass over V. Then after that, down here, this is because V is equals to AH. Okay, so I give it to you. Now from this formula, so what you need to remember, okay, maybe that's more important. What you need to remember is P equals to rho GH. This is not for solid, this is for fluid only. That means liquid or gas. So if you look at this formula, you will notice that the pressure for your exerted by your liquid or fluid depends on only three things: the density of the fluid, the gravitational strength, not gravity but the gravitational strength, oops, sorry, I spelled wrong, gravitational strength, and finally your vertical height, not just height but vertical height from the surface of the fluid. Okay, it does not depend on your cross section. It also doesn't depend on, for example, your slant height. So you may ask me, what is slant height? Well, for example, if you do this, and then if you do this, oh sorry, if you do this, and then if you do this, if the liquid level is the same, then the pressure underneath is the same. Okay, so it does not depend on this thing. This is called slant height. What is called vertical height? Vertical height is this. Okay. Then we can try to apply our understanding down here. Now, if you take a look at this, you will see that it is submerged and all that. I have to find the net force acting on the block. So if it is on Earth, then of course the block will be attracted by the Earth. You will have a weight. and as you can see here, there's a pressure acting on this surface, so therefore there will be a force here. Your force is equals to the pressure multiply the area. That is because P equals to F over A ma, right? So similarly, underneath here there will also be a force over here which is equals to PA. Now however, this pressure will be different because for liquid, the deeper you go, the higher the pressure. So because of that, let's call this F1 equals to P1. Then after that, here is F2 equals to P2 times A. So since the A is the same, I just treat it as the same. So how do we do the net force? We have to choose one direction as the positive, right? So I will just take, I don't know, let's take upward as positive, okay? Upward is positive. So here you go, I have my F net. F1 is going down, so it's minus F1. F1 is going down, yeah, minus F1. The weight is going down, minus W, and then plus F2. So my job is to actually find out what is the net force. So now I'm trying to find out minus P1A minus W plus P2A. Now I just need to substitute all the things that is inside. P1 is basically the fluid pressure exerted by this, right? So it will be rho GH1 times A minus the mass is 20, so this will be 200 plus rho GH2A. So far so good. So basically this pressure that is acting on the top side of the block is given by rho GH, and then after that under the bottom there will be pressure from the fluid, and then it will be also given by rho GH. So now what you can do is that you can put in all the numbers that you need. Density is 1000, so I have minus 1000 times 10 times A. Okay, A is 25 cm square, so I have to change. 25 cm square is kind of like 1 cm times 25 cm, right? Sorry, my cm square conversion, I need to do it step by step. So 1 cm is about 0.01 meter. 25 cm is 0.25 meter. So if I do that, I can actually convert my cm square to meter square. Doing this, it will be 0.0025 meter square. So now I have this. I can then put it in here, 0.0025 minus 200 plus 1000 times 10. Oh, I forgot the H. Sorry, that's the H. So now I need to put in the H. H is 0.05 here. Then here I would have 0.0025, and the H will be 0.07. Yeah. So if you calculate this, you will get a final reading. Make sure that it is 2SF. Okay, this final reading, I'm not sure is it plus or minus. But basically this question is to test you whether you are aware that this pressure is can be expanded to rho GH. Okay, so basically the first question just warm you up to that. Now down here is really getting into the working principle of a barometer. So for example, now I have this barometer and I name MNOPQ for 5 points, and I want to ask you what is the pressure there. So if now I ask you what is the pressure at point N, well, above point N is vacuum, right? Basically vacuum is nothing. So if I want to find pressure of N, it is equals to 0 lor. Yeah, can. How about pressure of M, O and P? Well, since they are on the same liquid level, they will be the same. Yeah, so let's take a look at the question here. Part A. Hence fill in the blank. When the atmospheric pressure is high, the height of the liquid column will be high lor. If now the atmospheric pressure is dropping, what will happen? It will decrease lor. It will become lesser. What is meant by atmospheric pressure of 760 mmHg? Well, it means that the atmospheric pressure can support the weight of a 760 mm mercury column acting over an area. Simple as that. Yeah. Or you can say that the atmospheric pressure is the same as the pressure under a mercury column that is 76 cm or 760 mm. So if you like that, you can also do that. You can say that the P atmospheric pressure is the same as the pressure exerted by a mercury column of 760 mm height. Okay, so how do I convert? Well, this is the conversion part. So P is equals to rho GH, right? So how much is 7720 mmHg? Well, I do not know, but I know that it is the same as, so this particular pressure is the same as the pressure exerted by a mercury column that is 720 mm high, right? So it's the same thing. Rho GH, I would have, so this is the pressure that I'm talking about. It is a column that is 720 mm tall. So therefore I will put in my density, then my gravity, and finally my height in terms of meter. So once I do that, I will be able to get the answer, and it has to be 2SF. Yeah. Okay, this one is to check whether you are a strong believer that P is equals to rho GH. So down here what happened is that the surrounding pressure, which is here, your P atmosphere, can now support a column of 1 square, 2 square, 3 square, right? It will support 3 units. So since it is the same atmospheric pressure, that means down here the pressure can support 1 square, 2 square, 3 square. It will support 3 units. So they are the same. Okay. So let's carry on checking on 8, 9, and 10. Basically, these last 3 questions, right, I really would want you to try it on your own first before you actually look at the answer. So please pause your video now and try it out before you continue. Okay, so let's begin with question 8. So question 8 here is that it says that this barometer is actually 40 because down here instead of vacuum you now have gas. So when we are dealing with a barometer, we always find a level whereby we say that the pressure of B is equals to pressure of A. So in your working, in your presentation, you must show me that you have this understanding. So once you begin with this expression, you will deal with the left hand side first. So PA. If you look at point A, what are the pressure that it is under? It is just simply pressure atmosphere, right? Because on top, there's nothing but the atmosphere. Now then after you do the left hand side, you move on to the right hand side. If you look at the right hand side under B, basically it is under pressure from this liquid column that is 620 mm high, and of course there would be pressure from the gas because now there is air molecules colliding onto the wall and all that. So your PB is actually consisting of 2 components, the pressure from the liquid column plus the pressure from the gas that has leaked into the vacuum part of the test tube. Now once you have that, you need to further expand it. So pressure from atmosphere, you are given that it is 760 mmHg. So I will write down here, your pressure is actually 760 mmHg. Now this pressure from liquid column, of course, normally you will expand it into rho GH to find out how much pressure that the liquid column is exerting onto point B. But since you see that on the left, it is the pressure now is given in terms of mercury column height. So in a way, this pressure from this liquid column, which is 620 mm height, you can simply measure the pressure from this liquid column in terms of 620 mmHg. And so you will want to find out your P gas, right? Can you see that now the unit is the same? So basically what you need to do is P gas is equals to 760 minus 620 mmHg, and you can use this as an answer. Remember, 2SF. Okay. Okay, for your 9A, basically it tests you whether or not you know where the H is measured from. Now, if you look at this case, the plane is actually experiencing the pressure from the top. So actually, when you are applying P equals to rho GH, you have to, P equals to rho GH on the plane, you need to know this length, this height, rather than this. Okay, so this is the tricky part. So now let's take a look. Okay, now we know that the average height is 18 kilometer, and the plane is flying at cruising high. Barometer here is showing 15 kPa. So this pressure that the barometer on the plane is showing is actually given by this height. So it is kind of tricky. Yeah. So now if you are aware of this, then when you write the formula P equals to rho GH, and if you go and write down here P is 15 kPa, then down here the G, it would be 18 kilometer minus H. Okay, so be careful. This is the part that it is tricky. The next tricky part is, of course, the unit. H is measured in meter rather than km, and this K is a prefix, so you need to take care of that. So if you expand all these things, it will look like this. Density of mercury is, or the density of air, because this layer is actually layer of air, right? It's atmosphere. So P, the rho is 1.1, G is 10. This will be 18,000 minus H. So all you need to do is you need to solve for H and then leave your answer in 2SF. Okay. Okay, finally, you will have another question. This question is very similar to this question, whereby you have different pressure on both sides of the same object. So down here, what happened is that the pressure from the cabin is different from the pressure from the outside. So this is your P out, this is your P in. Now we are analyzing force. So when we are looking at this general formula, how do we look at how do we get the force exerted by the pressure? Well, just make F the subject and you will get this. Yeah. So basically your F out, are they the same? Oh yeah, they are the same, because we have to keep this window plate in place. So the F out must be equals to F in. If they are different, then there will be a net force acting on the window, and the window will start accelerating and it will go off. You don't want that to happen, right? So down here, what happened is that the P out is actually lower, right? If I remember correctly. Yeah, so what happened is that because P out is much less, there is actually some screws over here, and basically these screws, right, will offset the difference between P out and P in. So let's see how to do this. So F out is consisting of P out multiplied by the area of the window plus the tensional force by the screw. Yeah, so the screw is trying to hold the window in, because your internal pressure from the cabin is actually higher. So you will have P in times A. So if you don't believe me, you can put in the number. Atmospheric pressure is 22.5 K. Okay, so let's do this. The outside pressure is 22,000 Pascal multiplied by what is the area of the each passenger's window has an area of this, so we just need to multiply by 0.050 plus I have 14 screws, so each screw will exert a force onto the plane. And what is the internal pressure? The cabin pressure is 78. So it is 78,000 times A, which is this. Now let's look at the numbers, and you can see this is the cabin pressure, this is the external pressure. So that's why your screw has to appear on this side to compensate the difference. If not, the window is going to accelerate. So what you need to do is now you need to solve for T, you will get the answer, and make sure that you convert it to 2SF. Yeah. Now this is the end of the first part of pressure. So to recap what we have done, okay, to recap, basically now we are in level 2. We now know how the liquid would react on pressure. We learn one new formula, and we learn how to use the barometer to actually measure pressure in terms of mercury. Okay, so this is how we learn the new formula. Then after that we learn this, then after that we now know that we can measure the pressure in terms of mmHg. So I think for this holiday we will pause here, and when you come back we will start on manometer. Okay, and we can throw in some demo to make your learning more fun. Okay, see you.